The two main startup commands that you would use to start up the bridge today are this first command here, and then there's a second one, which is for running the token swap demo. So this first command would start up all of our local infrastructure, including a Cardano DevNet, a local Cosmos chain that we kind of use as our entry point into the Cosmos ecosystem. And you can then use that chain to forward packets or vouchers anywhere in the Cosmos ecosystem. So that basically means that you can come up with a trustless voucher system for any Cardano native asset or any asset that is native to a Cosmos chain and have this trustless interop. I guess I'm gonna move forward with the presentation, not just do the live demo yet, just because there's a lot of kind of precursor knowledge. So if anybody's not familiar with Cosmos, Cosmos is a development kit that lets you build a sovereign blockchain pretty easily. There's a lot of out-of-the-box features if you don't necessarily want to reinvent the wheel. So you can get Tendermint consensus out of the box. There's accounting modules, basically everything that you would need to build a blockchain. So you don't need to be creative on all of those fronts. In the Cosmos ecosystem, it's pretty typical that chains will be application specific. So for the ones that I've listed, for example, Osmosis was one of the first main DEX chains. As of today, they still have the highest IBC volume. Checked is another chain that we're working with. They're doing some interesting stuff with digital identity. They're based in the States. And again, I would be curious to hear if anybody here has use cases for any of these abstractions, because we can make this bridge a bit more ergonomic to specifically whatever dApps people want to develop with these abstractions. Of course, there's DYDX, where you have perpetuals, and Injective is a Cosmos chain which has embedded a Solidity VM, and they also have either very low or zero gas fees, so that's a very interesting project. Generally, Cosmos chains will use the same consensus, so that's Tendermint, but they don't have to. For the purpose of today, we'll just assume that we're only talking about chains that use Tendermint consensus. So this is an interesting website that's worth checking out. It's called Map of Zones. QR code leads there. So this is like an interactive 3D map that will show you IBC volume all throughout the Cosmos ecosystem. So to just give like a quick primer on what actually is IBC, basically all of these chains out of the box have pretty low level interop, which is trivial to implement. So it's more about using out of the box features rather than having to like deploy some smart contract protocol. When we want to establish IBC for Cardano, Ethereum, Solana, those solutions end up being smart contract based. But in general, all of these projects basically get to do low level interop with each other in a pretty simple way. Right, so just quickly, even though these are all kind of out-of-the-box Cosmos chains, they still can have different runtime semantics. They can use COSM-WASM contracts. You could have Solidity contracts. You can define all of your own fee behavior. You can even do your own consensus if you want to. But all of these chains at a low level implement the important primitives that we need to kind of invent for Cardano. So succinctly, that's going to be light clients, connections, channels, ports, and packets. I won't go down this rabbit hole too much further. The way that I would divide IBC is into these categories. So IBC is composed of standards. So these are standards that are agreed upon by Cosmos or Interchain Foundation. It's kind of a like improvement proposal style process of finding the semantics that are the best fit for this low level interop, and specifically with IBC v2, which is coming, is the next version of IBC, is a slight simplification, and it's being developed in tandem with IBC Eureka. So this is the project where they're establishing IBC for both Solana and Ethereum. So I believe part of the motivation there is making IBC a bit more ergonomic in terms of integrating with non-Cosmos chains. Obviously, between Cosmos chains, it's pretty easy already. What would I say here? But yeah, so all you need to know here is just that these are the agreed upon standards, and that you basically compose this trustless voucher system via implementing these standards, which are basically agreed upon interfaces. I'm not going to traumatize anybody with a lecture about TCP, but the important thing to, I guess, remember if it jogs your memory is that there is such a thing called a TCP handshake. This is how a sender and a receiver kind of establish context between each other. There's like a step of, are you listening? Yes, I'm listening. Are you listening? Yes, I'm also listening. And then you can establish the context to be able to start doing information transfer. So we have a similar concept in IBC. IBC has kind of been described as the internet of blockchains, kind of based around this pattern. And I'm going to try and not go too low level here and maybe focus a little bit more on the actual APIs that you guys would be interested in to use the bridge. But this stuff is still worth knowing. So quickly, you deploy a light client. A light client is a mechanism for one chain's consensus to track the other chain's consensus. The way that is happening is through proof artifacts that are produced by consensus being relayed back and forth between the two chains. For chains like Cardano, Ethereum, Solana, this is generally going to be a smart contract protocol that is ingesting a Tendermint header. So that's like a lightweight data structure which contains enough information that a smart contract on another chain would be able to deduce whether a sequence of state changes is logical and provable. So once you've done this handshake, i.e. the two light clients are listening to each other, they trust each other's current state, then you establish a connection, so that just means the chains agree that they are listening to each other. A channel is the abstraction that allows us to send packets. So on Cardano, this literally just ends up being a UTXO. And within the UTXO, we are inlining some metadata, some information about what packets exist in the channel. Enough of that. I don't think we need to go too deep into these standards. I've already kind of explained. These standards exist, that's the important part. So here's just a quick visualization of what an ICS-20 packet flow actually looks like. So you can see that this is a voucher system, as I've described. Let me see if I can replay this again. So your token gets escrowed on one chain, a voucher is minted on the other chain. What you see, can you see my mouse? Yeah, okay. What you see here, this is called a denom trace. So that's information that's typically embedded in a token. It's a lot easier on Cosmos because Cosmos literally has a KV store, and you can basically arbitrarily store information on chain in a way that's pretty cheap relative to a solution that you would need for Cardano or Ethereum or Solana. Also, like some of these conventions are effectively stubbed. Like they're not very meaningful for the Cardano implementation. So what you're seeing in this denom trace is transfer, which is the port, and you're seeing channel 0. That's telling you the channel that this abstraction, this token arrived to this chain on, and then token would be the token name. So that could be Lovelace, for example. So core point is that the bridge then needs to understand when it's doing this ICS-20 transfer, am I sending a voucher or am I sending a native asset? So that's where the denom trace comes in. This string that we just talked about at this step. So basically, the bridge would need to recognize, am I actually minting something or am I burning something? Am I coming up with a voucher or am I just burning a voucher? So that's the core purpose of that mechanism. Right, so this is just a quick demo of ICS-24. The core thing to note is that the way we're proving state changes is via Merkle roots. So in this example, this IBC key that we're looking at is an example of something that you would try to prove that a channel exists or that the channel is open. So the channel would be comprised of two channel ends. One exists on each chain, and if you're trying to check, for example, does this channel exist, does this channel open, you're basically proving against a Merkle root that these channel ends exist on each chain. So this is just a quick demo of like what our overall bridge stack looks like right now. On the far right, you can see a list of Cosmos chains. End goal will be that you can add arbitrary Cosmos chains and bridge to whoever you want. These are just the Cosmos chains that we're talking to right now. Our objective would be either end of this week or early next week. We're going to have a pre-prod deployment of this bridge, and you would be able to point dApps at that and interface with these chains. Something that is still in the works is the exact semantics for cross-chain queries. So that would basically mean like being able to query arbitrary data from another chain in a way that is verifiable. So for check, for example, that's really important because they're doing a lot of compliance work, I think mainly in the States around digital identity. But you could, in theory, use their infrastructure to KYC. So if there's use cases where you would need certified data, maybe for a legal reason or even just for a general blockchain reason from another chain, we're going to be able to establish that. So just quickly, what we're looking at here, entry point, that is a Cosmos chain that we're using. So that is literally our entry point into the system. The reason that we're doing it that way is because we have to deploy smart contracts for Cardano, and we have a lot of proprietary logic that we don't want coupled with some other blockchain ecosystem necessarily. So this is like our one sovereign chain that we control. So we built a Mithril-like client, which adheres to the IBC v10 standard, and that is deployed there. Then we have Hermes. This is the canonical IBC relayer. So this would be like the off-chain piece of infrastructure. This is a cool project. It's written in Rust. And again, so the entire protocol is permissionless. So the idea is that anybody can run Hermes. There could be 10 of us, there could be 1 of us. Hermes can go down, all of your off-chain infrastructure can fail, and you're not going to corrupt on-chain state. So that's good. The gateway is just an SJS server. This is kind of where we're translating some of the proprietary logic. There's a lot of IBC constructs that don't really exist on Cardano, and we have no need to invent them. So you'll see things like revision number, which is an IBC concept, which we just don't need to use for Cardano. So a lot of that translation is happening there. Also in Hermes, we did do a custom fork, but we're potentially going to move away from that in the future if we want to support IBC v2, where I believe that the relayer semantics are going to change. And then there's, of course, Mithril, which we'll talk a bit more about. Yeah, I've kind of already gone over this. It's not as important. I'll also explain the primitives. Hopefully the primitives are clear at this point. Yeah, so this is the handshake that I was talking about. So for IBC, we have a 4-step handshake. This is just the process of the 2 light clients establishing trust with each other. Once they have completed this 4-step handshake, then we have the connection created, and now we can open channels, we can send packets, we can query data, etc. This gets a bit interesting for Cardano because of finality issues, which I'll get to, but we have some pretty heavy reliance on Mithril, which is also an open problem that I'll share later in the slide that maybe somebody will have a unique approach to, so that will be exciting to see. Right, so here I'm just kind of explaining what these constructs would do on Cosmos. We use them obviously in a similar way for ICS-20, but kind of like I said, port is less meaningful. I don't think we need to dig back through all of this again. Right, this is kind of what I alluded to about the off-chain infrastructure can fail because it's basically a packet networking protocol. So packets are allowed to time out, they're allowed to fail. They should still be delivered in the same order. Basically, part of being trustless means that there's no reliance on off-chain infrastructure, and there's no reliance that anybody would be running it. So in practice, a lot of Cosmos ecosystems are paying to have cloud-hosted relayers. So third parties are hosting those relayers. I think this is something that we're looking at right now. But it's totally fine if all of that off-chain infrastructure fails. If you were to, for example, bridge Lovelace to, I don't know, DYDX, let's say all of the relayers failed, there would be nothing stopping you from just spinning up your own relayer, pointing it at the 2 light clients, and then doing the transfer back. which is not ideal, but it's just to say you don't actually rely on a third party. Right, so I kind of discussed this before, but all of our proofs are Merkle proofs. So what that means is for us to certify a state change, we're basically certifying that a leaf exists or a leaf doesn't exist or that a leaf changed. I'll talk a bit more about how we're doing that, but the core point is that for Tendermint, we get really nice guarantees on a per block basis that let you do IBC with very low effort. On Cardano, that's not the case, and so having this idea of an authenticated root is a lot harder. We have a few nice design patterns, which I initially thought were very elegant and was very proud of them, and then it turns out that it actually serializes IBC operations, so that's a little bit less exciting, but we will get to that. Now I'm going to pull up a very scary slide that I want to say I did not create this, but there's a lot of arrows. This is from the Mithril team, so you can blame them if this is confusing. But core point for us, so we're using the aggregator and the signers. To jog your memory, if you don't know how Mithril works, the node operators are running signers. There's one aggregator. I'm not going to butcher a Mithril explanation in front of people who might know it better than me, but roughly speaking, we're going to pass around a digest of what your local view of the node is, and those who agree will sign the certificate. It's possible that you can have a certificate miss. Maybe people won't agree on what the actual view of the node should be, or that the ledger should be, rather. But when you get a certificate, it would mean that you can bootstrap a node and kind of join from this trusted snapshot. So that's kind of why for our stack, this first command that I showed, when you're running on a local devnet, you have this with Mithril flag because you actually need to run your own aggregator and two signers to be able to use this infrastructure on your local devnet. There's some important constraints. So Mithril has, I guess what I would say are protocol level constraints, and then there's configuration constraints. So for us, it's been pretty easy to kind of say like, hey, why isn't Mithril faster? But there's some pretty detailed improvement proposals explaining why the current configuration is the way that it is. And for what I'm going to describe about a 15 block cadence, for example, I just want to clarify that this is not some .env somewhere that is like setting a 15 block cadence. This is core to how Mithril is calculating Merkle roots. It calculates them in batches of 15. So that's something that's a little bit harder to change. We've been in contact with that team, but there's also a slight kind of misalignment there because we're using this for a light client, right? So we want to be able to certify state change on Cardano very quickly and granularly. That's ideal for us. That's maybe a bit of a push relative to what they were initially trying to do. So they, for example, lag the chain tip on mainnet by, I believe, about 100 blocks. That's pretty bad for us, but we're hoping to be able to change that in the future. Ideally, if there was more people participating in the Mithril network, if we had more signers, we might be able to push that a bit harder. That would help IBC a lot. But what this means is that on a Cosmos chain, we have certified state change on a per block basis that we can know is final. We can know that a supermajority of consensus finalized such and such a block. For us to get that equivalent guarantee, even on a subset of UTXOs for Cardano, is much harder. So that's kind of the abstraction that we've had to create. What am I showing? Yeah, this is just showing the Mithril cadence. So basically, what that means is if Mithril is producing a certificate, let's optimistically say it happens every 15 blocks, we can't actually rely on this state change. So semantically, IBC height is referring to the last Mithril checkpoint. Whereas on a Tendermint chain, every single height, you get that same level of guarantee that we can get from Mithril. And so to be clear on what the analogy is, Mithril, I want to say, is described as STM, so stake-weighted multi-signature threshold, yes. Stake-weighted threshold multi-signature, okay. So that's kind of analogous to what Tendermint is doing, right? Tendermint is passing around this header. We see someone proposes a block, the validators are voting on it. Once they reach 2/3 of the voting pool, that becomes the finalized block, right? So just to replay this really quick. So what that means is these validators are saying, I have finalized this block. So by the time that 2/3 have finalized this block, we can treat this as if it is final, right? Which is much harder to do on Cardano. But if I can show you how we actually ingest this, we now have this header, we pass it to our light client, and you can see that the light client can take this pretty lightweight data structure, and it's forming a chain of these trusted snapshots. It's kind of what we're looking at here. It knows what its last trusted state was, it's establishing a new trusted state, and we're going to continue this chain along. This is just how the IBC light client interfaces work. They have recovery methods, they have reset methods, they have trusting periods. So let's say your relayers went down and you couldn't relay these headers anymore, right? So we have our Mithril light client, you have a Tendermint light client, all of your relayers go down, and so they can't pass these headers back and forth anymore, and the chains can't really sync. They can't know what each other's state is. There's built-in mechanisms so that you can catch up. You could restart from a new trusted point and let all of your existing packets time out. You could provide a chain of missing snapshots. There's options there. The other core challenge here, you'll see in the trusted header at the bottom here, there's something called app hash. This is very nice. App hash is basically the Merkleized chain state of a Cosmos chain. So that means that for the entire chain state, you can very easily do this kind of proof that I just talked about, where you're checking if a leaf does exist or doesn't exist or changed in the last block. So that's super helpful for when you need this level of granularity, where you're basically doing packet networking, because you can literally check, does this packet exist here? Was this escrow done last block? And you can immediately trust it as fast as you can get that information, because this header is being produced on a per block basis. Whereas, like I said, we're only getting the Mithril header every 15 blocks. Yeah, so this is where we kind of explain why it's a bit uglier. Initially, the approach that seems the most intuitive, at least to me, was to try and certify on-chain state, which is not a good approach, because then you deal with actual finality issues and you're not able to rely on Mithril. So just to be clear, Mithril is not certifying on-chain state, it's certifying transaction inclusion. So our method here is that we tell the light client such and such a state change happened on our IBC host state. Here is the transaction where that happened. Here's what the outputs of that transaction were, which tell you what the change was. And it can then prove, yes, this transaction happened because it's in Mithril, and yes, I can deduce that these are the valid outputs of that transaction. There also has to be some validator logic to make sure that people can't arbitrarily mutate that state, but that's the rough idea. Yeah, I think I've kind of already gone over this. So I can explain a bit about the STC architecture. So the rough idea is we're trying to establish Tendermint on a UTXO set. That's basically the idea, which is pretty challenging. So what we've ended up doing is basically having a subset of the UTXO set where you're trying to establish a Tendermint-like dynamic. So part of that is you have this NFT, which we're calling like the host state NFT or the handler NFT. And you force all state mutations of these UTXOs to co-spend that NFT. So it basically functions like an on-chain mutex. The benefit of that is, well, okay, it's a two-edged sword, because first of all, that's going to serialize operations, which you arguably don't want. But this is the only way that you can have the same monotonicity that Tendermint guarantees. You need granularity over state mutations, because if you batch them together, you lose a bit of information as to how the rollback should happen. You lose a bit of information as to how transactions could depend on each other. For example, if you create channels get enumerated naturally. So if you have a channel 0, you could send 2 transactions on IBC. You could say create channel 0, create channel 1. You could chain these together so that when the second transaction arrives, it could see the first transaction's output and know that it needs to increment its own enumeration, but you can't base the state change on an already untrusted state. So before you build new state changes, you need to be building those state changes on an already trusted state. Now there's a question of like, well, could you just batch those state changes on Cardano together? I talk about that a bit further on, but it's a bit of an ugly problem. I'll come back to it. Right, so this is kind of what I've just described. Is you can think of this protocol less as moving tokens and more trying to reestablish the Tendermint proof artifacts on Cardano, where consensus is not playing nice, or rather is just simply not designed that way. Get along to my graphic here. Yeah, okay, so Tendermint natively satisfies three important IBC mechanisms. You have authenticity, so proving who signed the header. That means that on a per header basis, it's very easy to see that a 2/3 majority of the validator pool did sign this header, does testify to this state. Finality, so you know that there's only one header produced per height. So there's no question of like, is there gonna be a competing header? And this is again something that is called misbehavior in IBC. So for any light client implementation in IBC, you do need to handle like, what do I actually do if somebody tries to submit two different headers that claim the same height? The core mechanic is actually just panic, like know that something bad is happening and don't make any state changes. So it's not actually that easy to maintain, because IBC is based around Tendermint. You assume that these things don't happen and that you can certify state change based on the already trusted state. Right, and what authenticated root should proofs be checked against? So on Cosmos chains, this is pretty easy because you just have app hash natively. So it's baked into consensus that the validators are going to agree on what the last state was and what the current state change is. So that's very helpful. But like I'm saying, for us, we kind of have this surrogate. So kind of like I mentioned, this host state NFT, so that's an NFT that has to get consumed anytime that you touch IBC state. So per state mutation, you consume and recreate this NFT. Embedded in that NFT is our app hash surrogate. So that's a Merkle root, which is recalculated per transaction. Each time you remint that NFT, it's computing a new Merkle root based on whatever certified state changes happened in that previous transaction. Yeah, I think I'm beating a dead horse here. They're very different. Yeah, I think I'll push ahead here. Yeah, I kind of jumped all my slides. Wow. Okay, I'll jump ahead to the hard problem, because this is part of what I'm interested in a workshop context. So anybody can access this document. It's in the repo at docs host state UTXO sharding. It's a bit of a misnomer. We're not actually sharding a UTXO. Rather, we have two tightly coupled abstractions, which are deliberately coupled. But we're trying to decouple them in a way that lets us deserialize IBC transactions. So the question at least appears to be, how do you shard an on-chain mutex without sacrificing canonical state change and also unique monotonicity of state change? In this doc, I explain in depth how I approach this problem, what the current infrastructure is, and also kind of propose what I would say is like the naive solution, or the solution that seems like it works the best. But I also explain why it doesn't work. It's very ugly. It made me very sad. I thought I was going to find a nice solution, but I haven't yet. Also, to explain the batching issue is also that if you imagine what we're trying to do is, per state change, we're saying the last Merkle root was X, we're doing the state change, new Merkle root is Y. We can certify that the state change that gets us from X to Y is valid and it actually happened and it's authenticated, right? But if you're trying to batch multiple operations into this one Merkle root change, that means that, let's say we allow 10 people in this room to permissionlessly interact with the protocol. Any one of you could make a bad transaction or something that was inaccurate or malicious, and now the entire route change, the entire state change will be invalid just because 1 out of 10 was invalid. So it basically makes the protocol extremely easy to grief, even if you're not trying to do anything wrong, because your only option on a per block basis is either accept all of these batched as one change or don't accept any of them. Yeah, ugly problems. Yeah, I mean, this is just kind of reframing the same thing. It's like if you're trying to chain transactions, you need a certifiable ledger state as your intermediary step. So kind of what Giovanni and I were discussing is how you might be able to chain transactions like I was just describing, but your intermediary needs to be a verifiable ledger state. So that means it needs to be certified by Mithril, which is unfortunate because that basically means that anytime that there's a Cardano state change, we don't get to build anything on top of that until Mithril picks up that state change. So for us, this is quite a while at the moment. In the main README MD, I include relevant quotes from JP from Mithril. We had some good conversations with him where he kind of explained a bit of why things are the way they are, some CIPs about Mithril incentivization, which I think didn't get through, but there's a long conversation there. But Mithril mainnet configuration matters a lot for this bridge, so we're hoping that will change a bit, or that we might be able to find an alternative model. Yeah, of course, if anybody wants to pull up Mithril, this is just a QR code leading to that repo.
I have a question.
Yeah.
How will, with Mithril, you're working around the very long eventual finality of Cardano, right? Which is definitely mutability you only have after 2,160 blocks. How will Peras change the situation for your application? I'm talking a bit later, so I don't have all the context, but maybe I want to ask you now, speaking about Mithril attestation, the state of Cardano, how will that change if you have with Peras a built-in mechanism which tests faster finality? Like what's the thing you need, or how far of a finality guarantee you need? If you maybe look ahead or think ahead with like this Peras update. I'm not sure, hope you're say something here.
Yeah, good question. So my read is that I think Peras could lead to faster Mithril certificates, but that would still be our surrogate. We would still be relying on Mithril because the core thing is that, well, I believe the hitch on trying to do state proofs, there's this CIP 0165, which is about canonical ledger view. That explains a bit of why you wouldn't want to do like an Ouroboros-like client, for example. It's much easier and faster to just certify transactions, certify a state change based on some trusted route. But as for Peras, if I remember what I saw, it's that Peras can always revert back to earlier consensus. Is this true? Right.
If you
So
don't get the quorum of, I think it's configured 75%.
Yeah.
State, it's not active, right?
Yeah.
It's optimistic. Only when you reach that, then you get faster finality.
Right.
But if you have it, it's much, much, much stronger than what you have currently position in Mithril, right?
Yeah.
Julius, before you continue, you have five minutes left.
Wow. Okay. Okay. Interesting. So what matters? Okay, I'm running through all of this. This is just all of the hard problems that made us sad.
Just if I may add, like it's more subtle than that because Mithril doesn't give you fast finality. Mithril just gives you trust. For fast finality, you need that to be embedded in the consensus. So you will need Peras because Mithril signer can just lie.
Yeah.
Can just certify something and then decide to actually push a longer chain that will completely invalidate the certificates.
Yeah.
So in practice, like you do need Peras because that's the right certification mechanism.
Right.
And Mithril, I'm not. I mean, as a substitute, I think it's good enough for now, but it's probably something you want to replace with Peras once Peras is available.
You think so?
Yeah.
Okay. Okay. Interesting. So
Will Peras provide us like the possibility of building a live client for the attestation on the other end of the bridge, or do we still need? Because the nice thing about Mithril is that I know that there are some limitations, but it gives us like a certification says like, look.
Yeah, but it only
this
tells
happened.
you that people agreed on that. It didn't tell you that the data they agreed on is final. So So you do need pairs for the finality, and then you can use mithril to substitute trust, in a sense.
Yeah, so we still need a combination of the two.
Well, or you need a different trust source, but
yeah, correct.
right now mithril is kind of our only decentralized trust that we have.
Yeah.
Or need some kind of authority to say, well, I certify that this snapshot is on chain. But that's what mithril is for.
Because otherwise the alternative is to have like the full client on the other end, the full node on the other end, which we don't want. Like we want white clients, and mithril is the only solution. So we still need a combination of the two.
Likely, yeah.
Yeah.
So,
Thanks.
I will ask you more afterwards. Yeah, I guess we don't have much time left, but if anybody wants to reach out to me and Gio, if you want to talk about integrations that you're interested in or use cases that you're interested in, yeah, open book. We're happy to make the bridge more ergonomic to whatever people want to do. I think there's a lot of interesting use cases. Something that I was talking to somebody about yesterday is even the ability to, for example, come up with Cardano native abstractions for like DYDX assets, which would be like heavily leveraged futures contracts, for example. And if you're trying to create some kind of delta neutral trading strategy or delta neutral vault on Cardano, you could then use these assets to kind of get the adequate exposure that you would need without needing to pay spot prices. So there's lots of interesting applications. So can I pass you this for 1 second?
Yeah, sure.
So let me pull up. How am I going to exit this? Can I pull up Ghosty? Okay, so I'm just going to try and brother. I'll see this. Yeah, so this is just our basic command for starting up the bridge. Karabic is the CLI tool, which I think Giovanni first created. Karabic is largely just wrapping Docker commands and Hermes commands. Normally for IBC, you need to learn this entire Hermes interface, so we've kind of avoided that just so that Cardano people don't need to, learn a whole new interface. You don't really need to know it. It's just some basic infrastructure for managing channels and packets. Again, there's...
This is purely for Cardano, this one, the Karabic tool.
Yeah.
Okay.
Yeah. And there's still kind of some open questions. So on Cosmos chains, there's certain things that happen at application level that we don't necessarily need to do at application level. So for Cardano developers, for example, if people would rather have that, like, they can own a channel and nobody else can send packets on their channel, nobody else can close their channel, we can implement that kind of thing. It's kind of open to interpretation exactly how we would do it. I think that that's maybe advisable just because it can take longer to set up that infrastructure. Like creating a channel would take at least a few mithril certificates. So that's many. Huh?
About 30 minutes.
Yeah, Giovanni says about 30 minutes to create a channel. So it's like establish the handshake, deploy the channel, agree on state. So given that that's like kind of expensive in terms of waiting, it might be advisable to like give Cardano developers full like DApp control over managing those primitives. So it would still be a permissionless protocol, but you as a DApp developer would have complete control over the primitives that you're using, and like nobody could come and grief you. Maybe you could control who's allowed to send packets, that kind of thing. So I kind of did things a bit backwards. My initial intent here was to start with starting up the stack because it takes a really long time, but now we're doing it right at the end.